So I am going to try something new this semester. I am going to do the notes in the packet um, through a video. So rather than just going down and filling in the blanks to get the notes, you're going to have to actually watch the video and kind of do some stuff as we go along, because I think it will be more beneficial, especially as we get into some of the math and the more challenging things. So this first unit that we're going to cover this semester talks about chemical quantities and how we use chemical quantities to count these atoms, because atoms are so teensy tiny, very, very, very small, and millions, trillions, billions of them can fit on the head of a pen. Okay, so this first section is going to be kind of some background. It's going to talk about some of the scientists who were responsible for coming up with this idea of what a mole is and how we use the mole to count particles. We're going to review maybe a little bit on significant figures, and we're going to refresh our memory on dimensional analysis, because we're going to use that quite a bit this semester. Okay, so there are multiple ways of counting things. Okay, we can count items. Okay, for example, I could say I have 5 apples, or I have a dozen eggs. Okay. A second way, we could measure using mass. Okay, so maybe I would say I have 2 pounds of bananas, or I have a 16-ounce box of cereal. Okay, we will use grams. Okay, so we'll measure in grams of substance. And then the third way is volume. And volume, the volume we're used to are things like a gallon of milk, a pint. What we will talk about as we get into the scientific units, we'll use the metric system. We'll use liters, milliliters, things like that. Okay. So the next thing we want to talk about is how we can relate the mole to each of these measurements. Okay. Before we do that, though, we're going to talk a little bit of history. Okay. And we're going to talk about the scientists whose names are associated with this idea of the mole. And the first guy was Amadeus Avogadro. And I don't know if in your notes if this is what he really looked like, but every picture I see of him is just this scary guy, kind of creepy. But anyway, Avogadro was an Italian scientist who studied the behavior of gases, okay, so things in the gas phase. And what he proposed is that the volume of gas at a specific temperature and pressure contains an equal number of atoms or molecules. And it doesn't matter what the gas is, okay? So he kind of made that observation. All right. The next person that had anything to do with measurement and measurement of quantities was this guy called Loschmidt. Loschmidt. And he came up with this idea of the average diameter of the molecules in air. And he was able to calculate how many particles there were in a given volume of gas, which is crazy to me even today with our technology, that you could count these billions of trillions of atoms. Okay, and then finally, we get to Millikan. And he measured the charge on an electron. Okay, he's the one who figured out that the electron has a relative charge of -1. And based on that, he could look at a mole of electrons and figure out how to relate that to Avogadro's number, which we haven't talked about Avogadro's number yet, but we will. All right. And then there was a guy named Perrin. Again, we're just kind of going over this history. I'm not going to test you on it. The one name that I think you should know is Avogadro. He is the one that gets the most credit, and actually he gets the credit now that once he was dead, they didn't necessarily attribute it to him when he was alive. But Perrin earned the Nobel Prize for computing Avogadro's number using many different methods, and he named this number of particles Avogadro's number in honor of Amadeus Avogadro. And he used oxygen as a standard and proposed that Avogadro's number is the number of molecules of oxygen in exactly 32 grams of oxygen. Okay, the standard was later changed to carbon-12, and that is the present definition, is the amount of any substance that contains as many elementary entities. So what we mean by that are atoms or molecules, as there are in 12 grams, exactly 12 grams of carbon-12. All right, so a little bit of history. Let's see if I can pause this. Okay, so the mole, okay, MOLE, we abbreviate MOL, is a unit that allows us to go into the lab and relate teensy little particles of atoms to the grams that we can weigh on the balance. Okay. In Latin, mole means huge pile, which I suppose if you had a microscope specific enough, you would be able to see a huge pile of atoms. Okay, here's the number that you need to know. All right, the number is, or the conversion is, 1 mole is equal to 6.02 times 10 to the 23rd atoms or molecules or formula units. Okay, so this is a number that you need to know. And just for reference, okay, this number, and I have to count when I do it, if you were to write this out, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. It would be that many, okay? That many atoms or that many molecules. And if you want to know what that is, it's 602 sextillion. S-E-X-T, sextillion. Okay, it's a whole bunch. It's a whole bunch of atoms. It's a whole bunch of particles. Okay, there's a TED Ed, and I will try to remember to play this in class, that kind of talks about how big a mole is. Okay, but here's what we will use it for. Okay, it's an equality, like when we're doing dimensional analysis. Okay, it can be used as a conversion factor to convert particles into moles or moles into particles. basically the thing that we want to remember is that a mole, it's kind of like a dozen. Okay, if I tell you I have a dozen bananas, you know I have 12 bananas. If I have a dozen apples, I have a dozen apples. I have 12 apples. You also know a pair. If I have a pair of something, I have two. If I have a pair of shoes, I have two shoes. Okay, the mole is a number like that. The mole, when I say a mole, I'm always talking about this huge number, 6.02 times 10 to the 23rd. Okay, so if you look, we're going to look at an example. How many atoms are in a 1.22 mole sample of sodium? Okay, so we're going to kind of do this again. What do we know? We know that we have a 1.22 moles of sodium. Okay, sodium atoms. What are we looking for? We're looking for the number of atoms of sodium. Okay, and here's what we're going to do. We're going to set up a conversion. We're going to start with our known 1.22 moles of Na. All right. I always put this over 1. And the reason that I do it is people just forget, and they put some number down there. Just always put that first given, what you know, over 1. Okay. Then we're going to multiply. It's like we're multiplying a fraction. Okay. And we have to use this conversion factor up here. 1 mole is 6.02 times 10 to the 23rd atoms. Okay, so since moles is on top here, moles is going to go on the bottom of our conversion table. So 1 mole of sodium atoms is equal to 6.02 times 10 to the 23rd moles of sodium. Okay, now if I plug that into my calculator, and I guess just refreshing our memory, those units cancel out to give us atoms in the end. Okay, so if I do that math, let me plug that into my calculator here. I am going to do 1.22 times 6.02. Remember, we're going to have to remember where the exponent key is. Times 10 to the 23rd equals, so my answer is 7.3444 times 10 to the 23. So let's see, sig figs. My number here, excuse me, has 3 sig figs, so my answer can have 3 sig figs. So 7.34 times 10 to the 23rd atoms. So that's a lot of atoms, sextillion atoms. Okay. Okay, so that's an example of a problem that we can do. Let's look at another example. How many moles are equal to 4.79 times 10 to the 24th molecules of CO? Okay, notice the C and the O are both capitalized. That means that's carbon monoxide. Okay, so let's do this. What do we know? We know that we have 4.79 times 10 to the 24th molecules. I'm going to abbreviate molecules, MC. Okay, of CO. All that's, oh, then I have to do my unknown. My unknown is moles. How many moles of CO do I have? All right, so I'm going to set this up. 4.79 times 10 to the 24th molecules of CO over 1. Our conversion factor, we want molecules to go on the bottom. Okay, so 6.02 times 10 to the 23rd molecules is equal to 1 mole of CO. All right, so molecules of CO cancel, gives us our our number in units. Now this is where plugging it into your calculator gets really, oops, sorry, I had that down low so you couldn't see it. So pause for a minute, get this problem set up, and then when you come back, we're going to do this math. Okay, this is where we have to think about how this gets plugged into our calculator. Okay, we're going to take 4.79 times 10 to the 24th, and we've got to divide it by 6.02. So here's what you do. 4.79. I have an exponent key. Some of you have a second comma if you've got the TI calculators. But 4.79, I do exponent 24 divided by 6.02 exponent 23. All right, and this gives me 7.9568. Let's see, how many sig figs can I use? 1, 2, 3. So 7.95, this is bigger than 5, so I'm going to round to 7.96. My units are moles of CO, carbon monoxide. Okay, now here's something else. If you think about a mole is 6.02 times 10 to the 23rd particles. Okay, you would never have 6.02 times 10 to the 23rd moles, because that would be a really, 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 really big number. Okay, so that is how you should go about doing these calculations. All right, I am going to do, let's see, what do we got on the homework? There are 10 questions. So I'm going to do a couple of these just so that you have a reference, okay? So this one says how many moles are equal to 1.2 times 10 to the 24th atoms of sulfur, all right? So my known is 1.20 times 10 to the 24th atoms of sulfur. We're looking for moles of sulfur. Okay, so if I set this up, I start with my given 1.2 times 10 to the 24th atoms of sulfur over 1. Now we need to multiply it. So we need atoms to go on the bottom. So the number of atoms is going to be Avogadro's number. Okay, so 6.02 times 10 to the 23rd atoms, and that is equal to 1 mole of sulfur. Okay, so now I am going to do the math. I'm going to divide 1.2 to the 24th divided by 6.02 times 10 to the, try that again, 1.2 exponent 24 divided by 6.02 exponent 23. So if I plug that all in, I get 1.993355. 3 sig figs in my question, so 3 sig figs in my answer. My answer is going to be 1.99 moles of sulfur. Okay. I'm going to do one more example, and then I'm going to let you do the rest for homework. All right, so how many atoms are equal to 1.5 moles of helium? So we know that we have 1.5 moles of helium. We want to know how many atoms. So how many helium atoms? So we're going to put our known 1.5 moles of helium. Okay, now we need our conversion factor. Since moles is on the top, moles is going to go on the bottom. When we do these kind of calculations, mole is always 1. Eventually it will get to be something different, but right now, anytime you put down moles, it's going to be 1. And then 1 mole is equal to 6.02 times 10 to the 23rd atoms. Okay, so now I'm going to multiply 1.5 times 6.02 exponent 23. 9 equals 9.03 times 10 to the 23rd. Okay, and that is atoms. All right. So hopefully you could do these practice now. So I'm going to have you do 3 through 10 practice, and when we get to class, um, actually I'm going to have you try 3 and 4 for homework. And then when we get to class tomorrow, we will work on this. This is kind of going to be the way that I want to do things heading into second semester. I'll give you a video and a couple of problems, and then when we get into class, I will have you work more of the practice with me present so that if you have questions, you can ask. All right, so that is that. I will see you soon.